Now I'm going to introduce you another interesting K-partitioning clustering method called the K-Medoids clustering method. Why we need to study K-Medoids clustering method? Just because the K-means algorithm is sensitive to outliers, because the mean is sensitive to the outlier itself. Just give you a simple example. If you look at a company's salary, if you adding another very high salary, the average salary of the whole company actually may shift quite a lot. So let's look at the K-Medoids. What is K-Medoids? That means instead of taking the mean value of object in the cluster as our centroid, we actually can use the most centrally located object in the cluster, or we call Medoids. Okay. That means the K-Medoids clustering algorithm can go in a similar way as we first select the K points as initial representative objects. That means initial K-Medoids. The difference between K-means is K-means can select the K virtual centroid, but this one should be the K representative real objects. Okay. Then we put this one into a repeat loop. We can assign, similarly, we assign each point to the cluster with the closest Medoid. Then we can randomly select a non-representative object, suppose it's O sub I. We'll see whether we use O sub I to replace one Medoid M, whether it will improve the quality of the clustering. That means the total cost of swapping is negative. Simply says, if we're swapping, we can reduce the sum of the square errors. Then we are going to swap M with object OI to form the new set of Medoids. Then we need to redo the assignment until this process goes until the convergence criterion is satisfied. Now we'll see a small example on how a typical K-Medoids algorithm is executed. We look at the PAM as an example. Suppose we are given 10 small number of points in this small graph. Okay, in this 2D space, we want to find two clusters. At the very beginning, we arbitrarily choose K objects. Here we choose two objects as initial Medoids. Then we will find the clusters of these Medoids as follows. Okay. Then we will see whether we can randomly choose another object like O random. Say this non-Medoid object, we want to see whether it could become a Medoid if it will reduce the total cost, or we say we get a better SSE. In this case, suppose we choose one here, but we found it does not really reduce any, the total SSE. Then we actually can get another one, like we get this orange one. Then we look at the cluster we can form. We know this one will reduce the total SSE. That simply said the quality of the cluster is improved. Then we will do the swapping. Okay. So this essentially is listed here is we initially select initial K-Medoids randomly. Then we will do object reassignment. Then we try to swap Medoid M with the random non-Medoid object O sub I if it improves the clustering quality. Then we'll do it again and again until the convergence criteria is satisfied. So this is just a simple execution to illustrate the ideas of this K-Medoids, how it is executed. Then we'll see these K-Medoids clustering essentially is try to find the K representative objects or Medoids in the clusters. Okay. And the typical algorithm PAM called partitioning around the Medoids was developed in 1987 by Kaufman and Russo, starting from initial sets of Medoids Then we iteratively replace one of the medoids by one of the non-medoids if such a swapping improves the total sum of the square errors. That means the total quality of the clustering. This method works effectively for small data sets because we can keep trying different swapping, but it cannot scale well because the computational complexity is quite high. If we look at it into detail, actually this computational complexity for every swapping actually is to the square of the number of points. This is quite expensive. Okay. So how to improve its efficiency? There's one proposal by the same authors in 1990 called Clara. Essentially is PAM on samples. That means instead of using the whole points, we choose a sample S. S is a sample size. Then the computational complexity, this square actually comes down to the size of the sample. However, if the initial sample selection is no good, the final clustering quality could be poor. Then in 1994, there's another algorithm called Clarence proposed, is every iteration we do randomized resampling. That means we do not keep exact the same sample. We do randomized resampling. That will ensure the efficiency and the quality of clustering.